Welcome everyone to the inaugural DataFusion Community Showcase. Super excited for today's lineup of speakers. I think a couple of very interesting projects that I'm personally very excited to learn more about. And over the next few months, I think a lot of interesting things that I think many of us were not aware were currently being built on DataFusion. I'm Wyatt, one of the co-organizers of this showcase. I work with Spice AI, a data and AI platform, also built on DataFusion. We, I think, have a speaking slot in a few weeks from now, so excited to share more about what we're building. Shameless plug, we actually just announced Spice 2.0 earlier today, so if you visit spice.ai, you can learn more about that. Joined by one of my co-organizers, Andrew Lamb, as well as Luke Kim. Andrew, would you mind introducing yourself?
Yes, thank you, Wyatt, for organizing this. This is great. My name is Andrew Lamb. I'm a staff engineer in Flux Data and the PMC chair of DataFusion. And as Wyatt was just saying, all these great things we never really heard about building DataFusion. And once upon a time, I was like, oh, we should shoot for like, I don't know, 1,000 projects using DataFusion. And I feel like it's gotten to the point now where every day I hear about some new cool thing someone's building with DataFusion. So I'm super excited to have our speakers here today to kick us off and just tell us what they're doing. It's so cool.
Nice. So I guess just a few housekeeping notes. So we'll kick off. We'll go right into the two presentations. As questions arise, please enter those questions into the chat. Then Andrew or I, once we hit the Q&A portion, will read out your question or give you, I guess, first give you the opportunity to ask your question live. If you want to stay on mute, that's fine. Andrew or I can ask those questions on your behalf. But yeah, please stay unmuted throughout the course of the presentations. There's about 20 minutes dedicated to the presentation, and then 5 to 10 for Q&A. So that's the rough outline, but this is intended to be organic and free flowing. So yeah, super excited to kick off with Dewey.
Oh, yeah, thanks everyone for organizing this. This is very cool. I attended my first DataFusion meetup a few months ago in Boston, and I'm sorry if you attended that because this talk is very similar. But it was amazing to see all the things that people were building on DataFusion, live and in person, and seeing the sign up list is absolutely incredible. Um, and yeah, let's share my. Is that showing like my whole screen, or do you see like a big Firefoxy thing, or?
We just see the presentation.
Okay, cool. We checked this earlier. I just wanted to make sure I hit all the right buttons in the same order. So yeah, I work for Whereobots, and Whereobots, we're a spatial query engine basically, and a spatial query platform. But we have open source projects as well, and this is one of them. And this is the one that I get paid to work on all the time, and I feel so lucky that I get to write DataFusion code all day. It's called SedonaDB, and yeah, if you ever see me on GitHub, I'm PaleoLimbot. I used to be a paleolimnologist, and we'll see that in a second. So yeah, I didn't start out writing anything about query engines. I work on Arrow actually mostly, and that's how I got my start. I worked for Voltron Data, and yeah, I wrote NanoArrow, which is the C implementation of Arrow. During the course of that, I was working with Joris Vandenbosch, who's a GeoPandas maintainer, and Kyle Barron, who wrote GeoDataFusion and works at Development Seed. And we put together a geotypes basically for Arrow, extension types. And I spent a pretty considerable amount of time in R, working with geography and geometry in R. And most recently I work on Apache Sedona in that project and for Whereobots. So my background, and you'll see this come through in a lot of the stuff that we do in SedonaDB, it's really the whole stack. It's sort of from the lowest level of like how do we get things between libraries to like what do customers want or what are users looking for in a spatial engine. And of course, I'm also a geologist. And this is a very old picture. And I was trying to find the most rock friendly picture I could find in about 5 minutes. This is what I got. This is Newfoundland. And yeah, I have a PhD in paleolimnology, which is superficial sediments, but I also spent a significant amount of time looking at rocks and teaching undergraduates how to program and how to do GIS. I also am quite good at parallel parking, and we'll see this come through in a few slides. This is my old car, affectionately named Truck Truck. We spent a lot of good time. This is a parking spot that I felt particularly proud of in Calgary and took a picture of, which also informs some of the other things you'll see later in this presentation. So yeah, SedonaDB, if you look on our website, I think, what do we call ourselves? An open source single node analytical database engine with geospatial as a first class citizen. That, of course, we had to come up with something for the description on the repo, but you all know what DataFusion is, so I'm just going to put it out there. We're a bunch of DataFusion components. DataFusion was designed to be hackable, and we hacked the living daylights out of it to make spatial users hopefully very happy. And an important bit of here is that we're also all about the interface. So I'll show Python, R, and SQL here, and this is very important because these are the languages that people are using to do spatial analytics on their computer, and that is what SedonaDB is for. It's for being on your computer. It's a single node engine, and it's for getting yeah, I'll do it. It's for getting shit done, and so we hack. We hack living daylights out of DataFusion. Not that hard because DataFusion is great and designed to do that, but to make that happen. So this is one example, and it's very tempting in these kinds of presentations to just like try and list all of the stuff that we can do, and I'm going to try not to do that. I'm going to tell you the story of one query, and this is counting parking violations. As you can imagine, being somebody who pushes the limits of parking, as you can see from my previous picture there. This is something that I care a lot about, but also this is the subject of a blog post that somebody wrote. I think it was like maybe four-ish years ago. Somebody was like, okay, I've got these like 9 million parking violations for the city of Philadelphia, and I want to figure out which neighborhood has the most. And this is like a pretty classic spatial problem where you have two spatial tables, layers. You call them layers if you come from the spatial world, but two spatial data sets. And you want to know what the interaction is between them. And of course, just like in regular SQL, this is a join. You're joining two tables together on a predicate. And if you try to do this join without a specialized implementation, this will take forever. It will not finish. And if you don't use all the cores of your computer, this will take a very long time. Or if you store your geometry inappropriately, it will run out of memory. So this is like not that hard of a problem in the grand scheme of the world, but it's something that hadn't really been all put together into into a unified interface. So yeah, we're joining. We have the spatial join because the join condition has a spatial predicate in it. ST covers is the one. And we're grouping by, we're counting the number of violations. And so these are names of districts in Philadelphia, and you get a count of the number of parking tickets that got issued. Of course, I was not in Philadelphia at this time, so none of those are me, but I probably did get issued one at a different time in 2016, which is when this data set happened to exist from. Yeah, so also you might not be working in Python and you might be working in R, and so you can do that too. In R, we actually, the data frame story is a little bit easier because there is a unified data frame interface in R called dplyr or dplyr, depending on who you ask. And there's sort of these verbs, join and group by and summarize and arrange. They're all defined for you, and all you have to do is implement them. And of course, DataFusion can do this beautifully. And all the syntax is sort of covered for you in a way. So this was actually the easiest interface for me to write, also because I spent more than most time in R. But also maybe you want to write SQL. I don't, but maybe you do. But lots of people, particularly those coming from PostGIS or from other database engines, they feel very comfortable in SQL. And so you can do that too. You can make a join, and you can have a join condition, and you can group by, and you can order by, and you can aggregate. And we'll talk about all the components that made this possible. Backing up, of course, to how do you even get this? And this was something that was also very important to us because there are lots of different ways to like piece together spatial components, and some of them require installing various libraries, or some of them involving like PostGIS, they involve having a server. It was very important to us to just be able to install it. And so if you're In Python, you can pip install. If you're in R, you can install that packages. And if you're in SQL, we actually haven't quite gotten this yet, but you'll be able to DBC install and use their shell. Um, the folks at Columnar, they put together a shell terminal so that we don't have to like fork and modify DataFusion's excellent terminal. We did that for testing, but you shouldn't use it. When we get this together, you should be doing this because they have done a great job. There doesn't need to be that many SQL terminals in the world, and there's not much spatial specifically you can do from a SQL terminal like you can in Python and R. And of course, you have to read stuff. So I just at this presentation, I remembered that we forgot to implement read CSV. So you have to issue a SQL statement for that, but that's a fine way to do things. You can issue a SQL statement and read that in as a lazy data frame. And you can make that, in this case, we get sort of longitude and latitude, and we have to make our spatial column. But of course, you can read Parquet files or GeoParquet files, and we'll talk about what the difference and why we needed to special case those. And you can also read pretty much any other spatial file format. We interface with GDAL via some other Python package, the same one that GeoPandas uses, Pyogrio, maintained by Joris. And that, they support arrow already, so it was very easy. We just kind of reach in and pull their arrow, the arrow file. So this is super, and it reads URLs too, which is another important feature for me, because I can't be bothered to keep all of these sample files on my own computer at any given time. Yeah, and you can do this in R. It looks vaguely the same, and also you can do this in SQL. We're working on the geo package and shapefile and all the other GDAL file formats at the moment, but it will be possible to sort of read any spatial file and also any file that DataFusion supports, which is also a lot of files, important ones. So yeah, but also we're just DataFusion components, and this is a DataFusion talk, and so I'm going to use some DataFusion terminology. So if you're a user, that first bit probably really matters to you. Like this is something you can download and use, and you can type stuff. But if you're working with spatial data in DataFusion, we also provide components, and you can use those components if you want. So far, I think that people are using our spatial join and our scalar UDFs, as far as I know. But also, please let us know if you're doing that because it helps us optimize that use case. So yeah, I'll start with the scalar UDF. Then these are not the most complicated thing. You put some kind of spatial thing in and you get some kind of spatial thing out. Most of our UDFs involve either spatial in or spatial out. But there are actually a lot of these. So if you look at PostGIS catalog, I think there's over 200 of them, but we have about 176 as of our last release, a handful of aggregate functions. These are the things like stbuffer, stpoint. They usually start with st because there was a standard published in 2003 that said they should, and nobody has looked back. So yeah, it also helps with the autocomplete, right? You start typing st and you get a list of the spatial stuff. And yeah, so there's a lot of these. The last time I gave this talk in Boston, there were 88, and I haven't added any of them. I think I've added one personally. So this is actually one of the coolest things about has been the coolest thing about working on this project is that these scalar UDFs are an easy target for contributors, and so we've been able to get a lot of contributions and involvement by having people implement these and seeing how fast they are, which is fun. If you dive a tiny bit deeper in the internals, and I won't do too much of this, but this is basically what we're doing, right? We're implementing a scalar function. At the time that we started this, and I think even now, the signature system for DataFusion doesn't have anything to do with extension types, and we are an extension type. We deal with geometry. So we have our own Sedona type, and we have our own matching system. So pretty much everything is in any kernel, and we match from there and give our error messages and do our kernel matching like that. And another thing that is actually unique to spatial is that we have some completely wild libraries that are unrelated to each other. Like there's one called GIS that has a license that's not compatible with default distribution. There is one called S2, which has like the most horrible static linking thing you can imagine and only has C++ bindings. Um, there's sort of a huge variety. And so basically we piece together all these kernels, and some other systems work like this, DuckDB works like this. We piece together all these kernels, and so you can have like 3 or 4 ST buffer implementations, and and you can wire them in at runtime, and it'll sort of choose the one that applies to your types and was registered last. Yeah, also file formats. So the main one, Parquet, like GeoParquet was a massive improvement for a lot of use cases in the spatial world. And like you are Parquet people and DataFusion people, and you know this already, but we didn't. And so over the last, I think starting in 2000 was when these conversations started happening. So the spatial community made a metadata standard, and it was very widely. It turned out it was widely adopted. So you can read these things from BigQuery, lots of places, pretty much everywhere that can read Parquet files understands this metadata standard. Uh, but of course, if you read a regular Parquet file in DataFusion, that's not going to happen. And so we do have a wrapper around the DataFusion Parquet reader that also handles the Parquet types and predicate pushdown. And I think that's about it. On the rating side, there's also a bit of a shim to rate the statistics for all the types. You can write geometry without this, but you cannot write geography without SedonaDB's writer. And that was just a matter of the dependencies that are required to make that happen. Um, and yeah, so there's like a ton of spatial file formats. There's point cloud formats. There's GeoPackage. There's 20 years of evolution of spatial files supported by various people. And the main thing that they all support is predicate pushdown for a spatial filter. So like you're looking at a map and you want these features. That's actually pretty hard to do, getting a predicate that is not built into DataFusion across that boundary. And so we do have a way to do that, although we're hoping that we don't have to for that long. And when we figure this out, we're hoping pretty much any of this actually. When we figure it out and it works for us, we're more than happy to upstream this into DataFusion or wherever else needs it. And the joins are huge, as there's a lot of work that happens in joins in DataFusion. I think there's definitely a handful of different join implementations for non-spatial types. And of course, when you have a spatial type, it gets even more complicated. You have 2 dimensions. And particularly if you would like to execute something that's bigger than memory. So if you have this came up last time for me when I was deduplicating points. If you want to deduplicate 130 million points, I think you need about 24 gigs of memory. And like my laptop has 24 gigs of memory. So when you hit that point, you need to spill the disk. And spilling to disk in a way that does not absolutely kill performance is very difficult in regular joins, and it's difficult for spatial too. And that's something that was very, very important for us to handle for our customers. But also something that's just nice to have. Someone opened an issue not too long after we did this, and they said like, oh yeah, we're actually handling Parquet files with tens of millions of records on executors with 3 gigabytes of memory to save money. And your implementation is great. And like that's like we had no idea. We didn't make it so that other people could launch Kubernetes clusters and compete with us, but they did, and they did a great job. And they also contributed back and helped us out. And yeah, we needed an interface. So like we needed geometry to get printed when we printed tables. And geometry is like usually unwieldy long. So I think the default printer for Arrow just kind of like just barfs characters until the field ends. And we obviously needed that not to happen. And so we have a table printer. It's okay. We needed the schema to show like the things that people cared about. So like they care about what the CRS is of where this thing is, what the coordinates are, like when they're the X and Y values, how they relate to the face of the Earth. We needed like 2 pandas to be a geodata frame. And that is, something that we needed a special case. We needed a special case when people like had a geodata frame and like wanted to query it. Like it needed to show up as geometry and have all the right attributes. And yeah, and this is something that I added in the last release, and I'm pretty excited about it. Like we needed like a decent autocomplete story for spatial functions. And so like on spatial functions, like sure you can extend lots of these things. Uh, but it's like it's really hard to get the functions and like know what all of them are and also know what they're supposed to do. And like having this thing like actually give you the target CRS and like the list of that function is is really nice. I always forget what all of our 176 functions do. And I also don't want to write our documentation more than once. So we have documentation that's for SQL and R and Python. They're all generated from each other, which is super nice. Yeah, and it works in R too, which is important for me because I like R. Sometimes I feel like no one else cares about R, but I do. Uh, and yeah, dplyr makes it really easy to make the interface, but we have all these SD functions for autocomplete reasons, and you can get the inline documentation and look at examples from there too. Yeah, and this is actually not new. A lot of these things has been done before. And so I just wanted to take a second to talk about that. And for one, it's fast. Like we did this because we wanted to make it fast. We have customers that expect us to be fast. We're a spatial query platform, and so this shows up in our internals, and it's fast. We need a whole benchmark framework, and obviously we won it when we first put it out because that's how it works. But we're actually not winning it anymore for a lot of these. But we scale. We're the only one that can kind of get beyond SF scale factor 10 for this. This is using, I think, Andrew's favorite project, the TCPH generator, although it's not quite as uh, smooth because we have to inline spatial column into it. Yeah, but like, so I just put together a slide how we relate to some of these projects because I think it is important. We're not trying to replace any of them. We're PostGIS, but like PostGIS is, on a server somewhere and we're embedded in your process. So PostGIS, if you're updating your tables and stuff, it's great. But also the cost to load a table into PostGIS is very high. And so that's what we're eliminating. You can do all the same queries as PostGIS, but you save the table load cost. DuckDB Spatial, Max is great. We've chatted a lot, and a lot of the ideas in SedonaDB came from Max after he had a few beers and I had a few beers. But yeah, we are basically completely focused on spatial, and so I think eventually probably a lot of the functionality will converge. Um, but yeah, they're not focused on spatial. They don't have a spatial interface. Um, Somebody will probably make one at some point, but they haven't yet. And most importantly, they can't make Spark faster, which is what we needed. So, um, and yeah, so like GDAL, so obviously also built on DataFusion, also has to do with geo and geo functions. But we focus on the engine and the interface, and GeoDataFusion is very specifically focused on the components. I think Kyle would back me up on that like that is their focus. Like they're trying to provide these reusable components, whereas we are like very specifically not trying to provide reusable components, although you can. We want to make an engine, and DataFusion let us do that. Yeah, and we're still doing a Spark, same project, but we don't need a Spark cluster, and that's huge. So yeah, yeah, I want to acknowledge Tim Saucer and Andrew have done huge things for us in various PR review capacities, but also the whole DataFusion community has really stepped up. Adrian as well for metadata and making sure that all the things that we need to work to have our metadata go all the way that it needs to go. Somehow it's all metadata. I guess where it needs to go. And also the Sedona community. Like I did a lot of PR review and the main person doing PR review, but other people did a lot of the work. Yeah, I'd be remiss if I didn't show a spinning globe.
That was great. Thank you so much, Dewey. Does anyone have any questions they'd like to ask? So I think we got like 3 minutes before Alex is up. Or accolades they would like to give to Dewey or any other comments? There's a whole bunch of emojis going on in the chat if you haven't seen those, but
I'll take emojis. It's great.
yeah. All right, well, I'll wait 1 minute in awkward silence, and then if we still have awkward silence, we'll just move on to Alexander. I'm not sure I can actually wait a minute.
Yeah, you cut it off after at least 15 seconds. Yeah.
Like
all right, let's
they teach you like in meetings to like facilitate them really well. You have to like as a manager just really embrace the awkwardness so that people feel comfortable, speaking their mind. It's so hard to do. I always talk over it.
There's a reason I left managerial responsibilities several years ago, among other reasons. So without further ado, how about we hand it over to Alexander? Thank you so much again, Dewey. It was great.
Thanks. Yeah, thanks so much for the opportunity, and thanks so much, Dewey, for that excellent presentation. I'm bad at Zoom, so please, be nice. My name is Alexander Morose. You can call me Alex, or you can call me Al. Today, I'm talking about the idea that geospatial operations are actually relational. They're relational operations, and this is an introduction to my project, Xarray-SQL. If there's one idea I can leave you with in this talk, it's the following. My thesis is that with the right data model, basically all geospatial and climate operations could be done entirely in SQL without specialized libraries. A lot of the geospatial ecosystem is built around the geospatial data abstraction layer, or GDAL, and like the conventions from PostGIS, which set the precedent for the entire community, I think are wrong. As an outsider who may be totally wrong myself, but I think that they're wrong. And I think that they were decided at a time where there were hardware constraints and there were systems to make things efficient, to actually work in the computing environment of the time when the standards were made. But that computing environment no longer exists. That hardware has gotten really good, and we also have cloud optimization. And for those reasons, I think we should rethink the way we think about climate and geospatial data management. With that, I'll give an outline for what I'm talking about today. I'm going to talk about, in 3 acts, I'm going to talk about introduction to my project, Xarray-SQL. In the next project, I'll talk about specifically trying to back up my claim that climate and geospatial operations really are relational. I'll do that with a demo. And if I have time, and I'll try to leave time for questions, I'll talk about a new concept I'm trying to coin called differential databases. And it's kind of the future work based off of the premise of if we can do climate and geospatial operations, what else can we do? On the right here, you have the entire short story by Borges on the exactitude of science, where cartographers made a one-to-one map of the territory of the empire, and when the map faded away, so did the empire. Although that's quite a SparkNotes version of that story. I recommend this Borges story. About me, I'm a founding member of technical staff at Open Athena, which is a AI lab that's trying to partner with academia to do AI for science. In the past, I worked at Google Research on AI weather models. I've been an open source contributor to the Pangeo project primarily, and also some projects in Apache. And Xarray-SQL and all of this is my side project, and it's just an experiment, so please take everything I say with a grain of salt. In the first act, I would like to explain what Xarray-SQL is for those who don't know the project or don't know Xarray, assuming that we are just primarily a community of DataFusion people. And with that, I'll also explain a history of weather on Earth with a particular data set that I think a lot of these tools were built around. So here's a collab, and I can link it in some sort of a link place. I would like to talk about Xarray. I think it's a good premise. It's the other half of, I think we all kind of understand SQL here, but Xarray might be new for many people. Xarray is a Python data frame library. It's kind of like if you had pandas, but you had it for ND arrays. Pandas, compared to like CSV or just flat 2D arrays, it added like naming. It took the R panel data structure and brought it into Python. In Xarray, it has a data model representing any sort of ND array as follows. You have orthogonal dimensions, which are like the dimensions, like you can imagine if you're imagining an image by comparison, it's like the height and width of the image. In our case, in weather, for example, we might care about latitude and longitude and time. You have coordinates, which might be compositions of dimensions. Latitude actually might be a composition of X and Y direction in like a orthogonal plane, but we can also think of them sometimes as latitude and longitude depending on the context. These like 3D positions define an array of that dimension, and then per each value in that cell, you might imagine that there's voxels, which are like, you can think of color channels for an image, but in scientific computing, you might have hundreds and hundreds of values in each voxel. Like in weather, for instance, I'll show a data set that is just like that. And here you can see that there are an ND array that are the dimensions of the array, and these, like kind of in various parts of database literature, also are attributes. Here, you have a gridded raster. A gridded raster is this dense array for precipitation, for temperature, and Xarray is a data frame library that I'll show right now, and I'll show you the interface it makes. So here I import Xarray as XR, which is convention. I open a cloud optimized file format called ArcoEra5. This is analysis ready cloud optimized ECMWF, which is a Met Stations reanalysis, which is like a history of a ground truth of what the weather is, 5, their 5th reanalysis. And I open it without Dask. Here you have a bunch of dimension coordinates. You can see here that the time goes from 1900. This data set actually is valid from 1940 all the way into the future of 2050. So the data set is actually, it goes all the way up to the near the present, maybe off by a few months. And there are latitude values. This is latitude is 721, so this is 90 to negative 90 at a 0.25 degree or quarter degree resolution, and same with longitude. And pressure levels. So levels, this talks about the millibar pressure, which is a vertical distance of the atmosphere. We go from the surface, it actually should be first, should be in reverse order, all the way up to the upper levels of the atmosphere. And then for each of these dimensions, you have all of these different data variables that people care about that are meteorologically relevant. Like, the most intuitive ones might be 100 meters from the surface. You have the U and V directions of wind, their velocities. You might have dew point or temperature. Dew point is like a measure of temperature and humidity, and so on and so forth. And you have both mixed in here surface variables and atmospheric variables. This is the Xarray data set. I didn't quite explain, but it's a cloud optimized format, which means in this data frame library, in those modest few lines of code that I used, I'm actually now have control over, this is 1024 to the 4th. So this is 3 petabytes of data that I have access to, and I can play around with and do scientific analysis or visualization. And in the Python community, you can do things like select specific variables with a dictionary lookup. A cell is like a type of indexing operation that's named, kind of like in pandas. And here I can plot a view of the temperature in the new year at noon on 2020, New Year's Day. With just a few more lines of Python using a plotting library, hvplot, I can collect a wider slice of time. I can go from the beginning of the new year to 3 days after in 2020 and iterate through time, and then get something like a video or an animation anyway, as long as my notebook, you can tolerate a warning here or there. This is what the Earth looks like, the change in temperature over this 3-day period that you can get in plotting. So this is a pretty powerful tool that you can do with analyzing scientific data. This is the power of Xarray. The next thing I'd like to talk about is my project Xarray-SQL. It's a library that builds on Xarray and incorporates DataFusion Python. I guess I already loaded this. I shouldn't have reloaded it. But anyway, I have my interface, my API for this library is very modest. I have a context, an Xarray context, which is a DataFusion context. And I have all the normal functions that you can imagine, but I've added from dataset. That lets me get an Xarray dataset that I've loaded. I have to define a partitioning scheme in Xarray parlance. This is called a chunk, which is like a way you would iterate in a streaming fashion through an ND array. In DataFusion, like we keep the column orientation, but we define how many rows are in the column per each chunk. And then I also have some sugar to take these dimension names that I have up here in the Xarray dataset. Like here, most of the variables are by time, latitude, and longitude, sometimes time level latitude and longitude. I have some sugar that I can give them a more manageable name inside the SQL context. So here, the data set is called ERA5, but I can map the dimensions to a surface table or atmosphere table. And this takes about 10 seconds to register. It is a big data set. When I show the tables in my catalog, I have 2 surface atmospheric tables in the database. And this is what I mean when I say every ND array can be represented as a 2D array. I actually think of the orthogonal dimensions in Xarray as primary key columns in the table, and each attributes or data variable in the Xarray parlance as other columns that are non-primary key columns of the columns of the table. And it's one really long table, even though it's a gridded raster. I just talk about basically every point or every sets of points in that huge raster. And I can do the same for the atmosphere, where it's latitude, level, longitude, time. Why might we want to do this? Well, the reason is that it's really nice to express mathematical operations on top of gridded rasters as arrays. So here I'm taking a common calculation, which is I'm taking the data over the atmosphere, taking the temperature at every level of the atmosphere, grouping by level, filtering to the New Year's Day and 5 hours or 6 hours after New Year's, and grouping by level. So here you can see I have a calculation that's really common to do in climate science, which is trying to measure the temperature in C of the atmosphere as we go from the surface all the way to the upper levels of the atmosphere. And you can see how they vary, although this is truncated. Also in this library, I've implemented a feature where you can do a round trip. So here I'm taking an aggregation of latitude and longitude, some spatial variables. I'm getting the average temperature in C of the surface in that same time range and grouped by, and now I can get out an X-ray data set for me to do with, including the metadata. So here you can see like the units are preserved, like which is an attribute on top of the data because I passed in a template. That is Xarray-SQL in a nutshell and what it does so far. With that, I want to make a bold claim. Like you might think so far that this is just a toy, that I can load a toy data set and calculate a paltry sum. But I actually argue that it's not a toy, and that the implications of this is that everything we normally do or do of substance in climate and geo actually can be done just with a simple model that's kind of as simple or silly as you can make it. This is the beginning of Jean Baudrillard's simulation to simulacra, where he refers to the Borges story and talks about how it's a perfect example of simulacra, which is a copy of a copy with no original. With this, I will load, I will show my README doc and also demonstrate my project. So I'm in GCP in US Central 1, which is close to where the data is. And I'll run some example scripts. So what are meaningful geospatial tasks that people might want to do? I didn't pick them arbitrarily. Actually, lucky for me, the DAST project, Coiled, tried to get a survey among scientists and engineers in the community to figure out what are the most valuable, to improve DAST in Coiled, what are the most valuable climate and geospatial operations that exist that are currently done by X-ray users or scientists in climate and geospatial that exist at the 100 terabyte scale that we could use to optimize this distributed system to make it work at this level. And we got a lot of answers from various engineers and scientists in the community. And I've basically abstracted all of these into a table of maybe 9 or so, give or take, core operations that are common operations that we might do in geospatial analysis or climate and weather analysis. The kind of word count of this, we do UV run, benchmarks, geospatial 01, is something called the NDVI. And NDVI this is actually taken over a real Xarray data set, a real satellite data called Sentinel-2, which is a canonical data set in geospatial. This is the SQL query that is needed for NDVI. The equivalent array query I'll demonstrate in a second. But NDVI can be expressed in Xarray on Xar really simply. Here's the main function. Here's the SQL statement. And then here's what it is in loading the Xarray data set. It's kind of similar in both frames. And I have a script here that proves you can do both in this column representation as well as the array representation down to floating point tolerance of equivalent as much of a floating point number as equivalent. And that is a good proof of concept of the simplest case, the word count. I've demonstrated a climatology, which is just a group by the thing that repeats the hour. But what's a more interesting motivating case? A climatology or an anomaly, which is like a variant of the difference of the climatology. Those just take a lot of time. I can actually do a difference of forecast. So here I'm comparing two AI weather models, GraphCast and PagNu against ERA 5, the ground truth, which you just demonstrated. It actually is just a really succinct SQL query with root mean squared error defined as the SQL function. The case where you might want to reach for SQL over an array library is this case, the raster vector zonal mean. So let me look at this case. It's actually 06, and I have a numbering problem that's a classic computer science error, which is off by 1. This is the equivalent array code that's necessary to calculate this statistic, which is like the statistics of an average within a region. This is hard to do in an array modality. You see, it's this complicated kind of like you have concats and these filters and a where clause and a mean that's complicated to do in an array paradigm, but trivial to do in SQL, provided you have the tables kind of set up that you can really trivially in Xarray-SQL. This is because we do one of the value add to the hardest things to do in in a physical representation of the data, which is joining gridded rasters and tables. Like that's non-trivially hard most of the time, but if all the gridded rasters were just tables, it's trivial to do. It's just a relation. And then maybe the skeptics, the first thing when I talked to a geospatial practitioner that they were skeptical about, that really all geospatial operations, maybe climate and weather, could be done with SQL, was the idea of reprojection and regridding. Can this be done purely in SQL? And the answer is no, but only with one additional user-defined function, which is pyproj. You actually don't need GDAL at all. All you need is a reprojection function, because it turns out that reprojection in this array model is a pure function on rows. With the reason why you want to do it not in SQL and you want to go to UDF is that it's a really complicated spec. To get all the coordinate reference system information right. You want to delegate that to an authoritative library. The other insight here is that regridding is not row independent, it's an aggregation, but an aggregation is just a group by. And we can actually, it turns out that to regrid, given that you have a projection, it's just a sparse matrix vector, a sparse matrix vector product. This is a sparse matrix vector product. It's a matmul. A matmul in SQL in this data model is just a sum over a multiple, joining on the dimensions of the proper dimensions of the matrix that you care about with a group by and a reduction. It turns out that this is the same as Einstein's summation notation, or an einsum summation notation, and this is maybe more verbose than einsum, but this maybe is more general and more elegant, in my opinion, depending on how much of a lover of SQL you are. Given all of this, it turns out that maybe the common thing that we usually use a platform for, a geospatial library, the warping, is actually just a pure SQL call with one UDF, which I am calling here. So in this script, and I'll demonstrate it, I'm running a warp function, which are the SQL statements that I showed you. But for reference, I actually use I'm not comparing pyproj against proj. I'm comparing it against Google Earth Engine's implementation via a library I wrote called XEE. And I show that I correlate with an independent reprojection library, geodesy in Java, via Earth Engine's platform, which is their implementation. I get a 98% similar reprojection on real data, on a real data set in Google Earth Engine, that my reprojection logic in SQL is like pretty close within like scientific tolerance, depending on the needs of the query. Of course, I don't want to claim that I can do everything, but I'll leave it up to you to define it in the reprojection function, or at least I will one day. At this point, I was like, wow, all geospatial and climate operations, they're actually relational. That's pretty big, but it got me thinking kind of a second. I actually took another look at the original benchmark here, and I kind of realized something, which is that all these, like, let's say climate simulation benchmarks, they're actually just post-processing off of something else. They're post-processing off of physics simulations or processing off of things derivative from observations. And I'm like, why can't the physics simulations be inside the database? Why can't we replace, GFDL, like the NOAA's, numeric weather computing with SQL and with a really souped up database? And I realized that the missing component that was necessary to do this, that I don't have represented in this model, is not linear algebra, it's calculus. That in order to do a real physics calculation, we need to have the ability to take gradients. And with that, I want to present my future work, which is something called differential databases or postmodern databases. This is from Logic Comics, which is a great graphic novel about computer science, talking about how confusing the map with the territory might be a good definition of insanity. So please, if you'll join me in the insanity, I will talk about another demo, which is I put AutoGrad inside a database, and I'll show it right here. Here is my neural network implementation. I'll make the screen big. So it turns out that AutoGrad is actually really simple to implement if you take it from the first principles. There's something, to calculate a gradient, you need a matrix of partial derivatives. It's called a Jacobian. But in the libraries where we do a Jacobian, in our data model of our type of representations of arrays, we only care about the diagonal of the partial derivatives, which means actually it's a row-wise function. Grad, the things that you do for calculus, it's a forward or backward pass Jacobian, and it turns out that you can do it column per column. And with that insight, here's a neural network, a 3-layer multi-layer perceptron. Here are the definitions of the layer sizes. I load the fashion MNIST data set, courtesy of Carbon Plan, which is a data set that looks like sample height and width in pixels versus samples and labels. The model is just another Xarray data set that I define as arrays. I can load the data set into the context. I can do a test train split to get a training set and a test set. I can load the model also as tables. I union the model so that it's actually a really long table of weights. I calculate over steps a forward pass. A forward pass is you take care of the bias over here in this A subquery, and it's the same mapmol that I explained otherwise. It's an INSUM notation instead of matrix and vector. It's a matrix mapmol, which is just a selects over some join and group by. I also do the tangent, funny tangent, the hyperbolic tangent, which is necessary for neural networks. I make multiple forward passes. I calculate the output logits, like the output layer. I calculate softmax, which is a definition based on exponents inside a query within with statements. I calculate the error term, which is I use case statements for an indicator function. Here I calculate the gradient version of that, and then here you can see here I've defined a UDF grad. All grad does is it takes the symbolic derivative, applying the chain rule of everything inside of it with respect to another column or a constant that you care about. And that's really all you need inside of a database to calculate derivatives. You can see here I have a real neural network running across 60 steps. The loss goes down, the accuracy goes up, and I also have the accuracy going up in the validation set or the test set, so I know I'm not cheating. And at the output, I output an Xarray data set that I write to Xarr, which is the same as a neural network like safe tensors or a PyTorch checkpoint. A weight update rule is just a deregistering a table and adding a table, and you can see I update the weights by doing a learning rate thing. I take the previous weight times the new weight. Well, anyway, I'm getting a little bit too into the weeds here. I think the point is still there, which is that we can actually make a neural network. So taking a big step back, JAX is maybe the simplest neural network framework out there, and I'd like to compare XQL or Xarray-SQL against it. JAX, the joke about it, the name is just AutoGrad and XLA. XLA is extended linear algebra. That means JAX is gradients, VMAP to handle the batch dimension, just-in-time compilation to compile to modern hardware. You need an array library and crypto, and that's it. And that's very, very simple. XQL or Xarray-SQL is grad, which is the same two Jacobian vector product, the vector Jacobian product. And I'm sorry if my calculus is wrong, please forgive me. Arrays are tables. They're just tables. And that means mapmols are this pattern, but otherwise there's no additional SQL, it's just the SQL language. And that's it. That's as simple as XQL, and that's all that you need. And you might be asking, like, where's JIT? Where's random and crypto? Well, I would actually argue that this is the promise of the relational model. The relational model says I can go from concept to a logical view of data and have that be independent. If I can explain pure mathematical relations, I can have a logical view of data that's independent of the physical view of data. Because we can express things as pure relations, maybe we have a chance of writing, compiling a PyTorch framework into SQL and having the physical model people figure out how to distribute it on 1,000 GPUs really, really well. That's I think why we might be cooking with gas here and why this is really promising. I will pause there or not go on. I have some ideas about what an ML model is and what a database is. A differential database, I think there's a so this is what the chart from Michael Stonebreaker is in the Red Book of what all the components of a database are. I think machine learning has proven there's a new database component, and it's like the differentiation or autograd inside the database. I think that machine learning models are postmodern databases. And anyway, that's all the time that I have. Thank you so much for listening to my ramblings. If you're interested in getting involved, I created a website called XQL Systems. There's a Discord link there. You can follow me on Blue Sky, and please pip install Xarray-SQL. Thank you so much.
Amazing, amazing. I feel smarter already. That was I think it's going to take me several minutes to process that. So I'll be doing that. While I'm doing that, does anyone have any questions we would like to ask Alex? So good.
I see there's some people in chat. Yes, so I did benchmark join versus ball, or the linear algebra pack. I always call it balls, but that's totally incorrect. Or BLAS is the correct name. These are sparse matrix. These are sparse matrix multiplications, and it's much slower than the compact, the physical form. But that's an implementation detail. That's for like Apache Sedona's efficient join implementation to do joins that are really efficiently for like with modest amounts of memory. We probably could take that almost off the shelf and put it in here, like the implementation on top of a relational model, and get something really fast. I think maybe all of the I see a lot of the state-of-the-art things that are happening right now in databases from like NVIDIA and across Apache DataFusion, like SiriusDB, are let's accelerate databases with GPUs. Like I think this conceptual model is right in just in time for us figuring out how to accelerate databases. The implementation is a lot slower, like with hash joins versus actual very low level CPU parallel things. But I am with Xarray, with the metadata of Xarray, I know where every byte is in like up to a petabyte of data, where it will be. In theory, we should be able to we should be able to GPU accelerate the crap out of the inefficient thing. But what's also crazy is that because it's a sparse implementation of a matmul, so like you could do crazy things. Like I have an optimization of the script I just demoed, where if the input is a 0, because you multiply any pixel by 0 at 0, I just omit the 0 rows. So it actually can make this query faster by omitting data that I know will be bad in a matrix multiplication, which is totally bananas crazy from an array perspective, that you can make an array multiplication fast by omitting the null data. Like you can't do that in NumPy, but we can do it in this, world of logical programming that we are in here. That mul pushdown, I like that.
So your idea is like that you'll have a specialized join operator to implement matmul or matrix multiplication potentially. That would be one avenue to explore from a performance perspective. Yeah.
Yes, and I guess when I talk about it, I think the question is also like on what computer. If the computer is a single node, you probably want a specialized matmul operation. But if the computer is a large distributed system, I think actually I would win. If you have the full 3 petabytes of that Xarray data set, that Xarray data set, I think I would have a better time scaling to all 3 petabytes using DataFusion in like Ballista or distributed with a really inefficient implementation, rather than trying to scale out like Dask as it is today, or scale out a thing that doesn't have we have, depending on, unless we're doing an unthing, but the 50 years of databases have gotten really good at query planning and scheduling on like hardware, and we can take advantage of all of that as opposed to having to reinvent it from first principles for a paradigm that is wed to the physical relationship of data, not the logical relationship. Join my Discord laboratory and we'll hack on things together. We'll do some mad computer science. I think it should be a lot of fun.
Yeah, it's great. I think the best talks are ones where you're like, now that he says that, that seems like obvious. Like, why wouldn't you separate those two things? But before someone said it, it wasn't obvious at all. So very nicely done. Yeah. I think someone's asking in the chat maybe to post whatever the link is to your organization. And I think with that, maybe I'll turn it back over to Wyatt and he can close this out. Thank you so much, both our speakers. Dewey and Alexander.
Yeah, thanks, Alexander and Dewey. I love all the contrarian angles, especially that you're taking, Alexander. Yeah, so we'll have the next Luma event published tomorrow. So we'll be meeting, I think it's at the same time. It's either 3 or 4 p.m. 2 weeks from today. And that's the plan kind of going forward, and meet bi-weekly on Thursday. So love to see everyone here back at future events. It'd be fun to build kind of a community around supporting other builders on DataFusion. Yeah, and I think that's it for today. And if anyone has any recommendations or would like to get involved, obviously there's not a ton of planning associated with these virtual meetups, but if you have recommendations for how we can improve going forward, I'd be very much open to that. I'll throw my email in the chat.
You know,
then-
Wyatt, and on behalf of Spice AI, thank you so much for planning and giving us a opportunity to present. Like, I really appreciate, yeah, getting to share the madness and also bringing the community together. I think it's cool when the good, cool, you know, software is so much about community, and these type of things are really important for that.
Yeah, of course. Appreciate that.
Yeah, that was awesome. Thank you, Dewey and Alex.
Alrighty.
All right, well,
I'll see you in a few weeks.
weeks. Goodbye.